Hello everybody, Leela Fries here with a presentation on ZOS storage performance and replication analytics. Although some of the material may be familiar to you, I believe you will find several tidbits that will be very helpful in your everyday job. I have 23 years experience in the storage performance trenches. Before joining IntelliMagic, I was the team lead in development for enterprise storage product performance at IBM. Now I am a senior consultant at IntelliMagic for both ZOS and distributed performance. Here is what we will cover today. I will start off with some background material on ZOS storage architecture and how it relates to performance. Then I will talk about some basic ZOS performance concepts, including response time components, I/O rates, and throughput. Next, I will discuss how to be more proactive when monitoring storage performance. Finally, I will review some techniques for finding bottlenecks in a storage system and draw some conclusions. So what is the only correct answer to any performance question? It depends. Almost every performance person I know has used this line to answer a performance question more than once. The sad truth is that performance is part art and part science. Although everyone wants simple rules of thumb, sometimes relying on these too heavily can get you into trouble. That is why effective performance analysts know what factors performance depends on and can look under the covers to get to the real root of the problem. If we look at modern enterprise disk storage systems, we see that all the vendors have pretty much similar architectures. They all have front-end adapters, sometimes called directors, to attach hosts or other storage systems, back-end adapters to connect to drives, either disks or SSDs, large cache memories, and a fast interconnect bus or switch to tie it all together. All the vendors keep 2 copies of modified data in memory for resilience and use RAID at the drive level to provide redundancy. If we go back to the disk storage architecture of the 1990s, we saw a great deal of serialization. This meant that as the storage became more utilized, we would see gradual response time growth, and that would help us to detect bottlenecks. With modern architectures, parallelism is everywhere. This keeps response times low until we reach a critical point when we will typically see a large spike. This makes high response times less useful as a proactive measure of storage health. For those that are new to ZOS storage performance, response time components may be a bit mysterious. This table explains the components in familiar terms by comparing to a telephone call. IOSQ represents time that the device is busy servicing another I/O. PAVs have introduced additional lines of service so we don't get so many busy signals anymore. Pen time means the phone is ringing but nobody's answering. For example, the storage system is busy servicing other I/O, so things are backing up. Connect time is associated with actual transmission of data, which is akin to talking on a telephone. Finally, disconnect time is associated with retrieving data from disk. This is comparable to putting someone on hold while you're looking up information. I/O rate and throughput are 2 ways of looking at how much work a disk system is actually doing. I/O rate is the metric most frequently reported, although throughput is generally a much more useful metric. But I/O rate is what most RMF reports provide. In addition, storage vendors typically use I/O rate measures when they're marketing their product. However, throughput gives a much better picture of how much work your storage is actually doing. Here we see 2 charts using real customer data. The first chart shows I/O rate and response time. There is not much correlation between those metrics. The second chart shows throughput and response time, and you can see that these metrics are much better correlated. At IntelliMagic, we see lots of storage performance data from numerous customers using disk storage from every vendor. Typically, the performance bottlenecks we see fall into 4 categories: front end, middle layer, back end, and peer-to-peer connections. The front end refers to the host adapters and ports that connect the storage to the ZOS hosts. The middle layer is the cache, processors, logical structures, and interconnects that exist between the front end and the back end. The back end includes the device adapters and physical drives that store data. Finally, the peer-to-peer connections are connections between disk storage systems that are typically required for remote data replication. Most shops need a quick and effective way to stay on top of performance and ideally recognize issues before they become problems or SLA violations. For this purpose, IntelliMagic has developed a number of performance dashboards that are included with IntelliMagic Vision. Here we see an example of a dashboard, this one covering the various disk storage systems in the customer's ZOS installation. Dashboards are designed to quickly point out where the risks in an environment are. This dashboard has a row for each disk storage system in the environment. Each column has a different performance metric. The dashboards are color-coded to provide key risk indicators for metrics that are frequently exceeding thresholds. A yellow dot indicates that a metric often exceeds the early warning threshold. A red dot is used when metrics regularly exceed the performance exception threshold. The size of the dot is proportional to the frequency of the problem. Blue dots are used for metrics that are not rated and have no threshold. In this case, the size of the dot is proportional to the intensity of the metric. IntelliMagic Vision includes dashboards for many other interest areas, including channels, LPARs, replication, coupling facilities, and storage groups. When you click on a dot in the dashboard, you drill down to a multi-chart with all the relevant metrics for that disk storage system. The border of the chart is color-coded to show the rating. In this case, a gray border indicates no rating applies. From the multi-chart, you can click and see a full-size chart. From there, you can drill down to even further detail, such as SSIDs, ports, storage pools, volumes, etc. One of the key features of IntelliMagic Vision is the ratings we attach to performance reports. Ratings are how key risk indicators are surfaced and provide an at-a-glance view of performance health. A rated chart is characterized by a colored border, with green being good, yellow an early warning, and red indicating there is a performance exception. Charts with a gray border or no border at all are not rated. Ratings are one way that IntelliMagic leverages their deep knowledge of hardware capabilities to provide availability intelligence, a truly proactive early warning of risks, not just indications of problems that are already occurring. And when an unpredictable problem does arise, the ratings help you shorten the mean time to resolution by guiding you quickly to the source of the problem. IntelliMagic Vision comes preloaded with thresholds based on hardware capabilities. Some of these thresholds are static in nature and don't vary by interval. However, just because they are static does not mean that they are based on just one number. The static thresholds are calculated by Vision based on a number of configuration variables. In this example, the throughput thresholds are based on the model of the storage box, the fiber channel speeds, and the number of ports and adapters. Notice that in this example, chart frame is red. This is because the thresholds are exceeded often enough that it indicates a problem. You can see the thresholds on the charts as shades of gray. The light gray or cloudy region indicates an early warning. The dark gray or stormy region indicates a performance exception. Thresholds may be adjusted if desired, and you have a good reason to do so. This chart shows an example of a dynamic threshold. Dynamic thresholds are workload and hardware dependent, and thus vary from interval to interval. This makes sense for a metric like response time, since the read-write mix, size of the IOs, and cache hit percentages can all affect it. Vision is essentially modeling what the threshold should be. In fact, you can see the actual response times follow along with the thresholds quite nicely, although mostly well under them in this example. Since the thresholds are rarely exceeded, this chart is rated green. Now let's consider the front end of the disk storage system. Host adapter or director bottlenecks are a frequent source of delays in modern disk storage. However, uncovering these bottlenecks can be pretty tricky. The host adapters provide connectivity to hosts and between storage systems. Although these adapters may support various protocols, for ZOS hosts, the most common one is FICON. For peer connections, Fiber Channel is typical, but other protocols such as iSCSI may be used. The number of ports available per card varies depending on the vendor and the technology. It is usually not possible to run all the ports on an adapter at rated speed simultaneously. In fact, most production workloads won't achieve rated speed even when using a single port on an adapter. Thus, it is not very reasonable to expect 800 megabytes per second out of an 8 gigabit port in production. Host adapters are stressed both by the number of commands they process as well as the number of megabytes they transmit. The larger the transfer size per operation, the more efficient the host adapter will be. Thus, it is quite possible to saturate a host adapter by running very many small transfer operations. Yet the host adapter would be able to handle much higher throughputs if the size of the transfers was larger. Today, FICON is the most common protocol used for ZOS host I/O. A FICON channel processes many I/O operations concurrently. However, the commands and data packets from multiple I/O operations are interleaved on the channel. At a certain level of concurrency, the pipe becomes full of data packets. When this happens, additional concurrency elongates the transmission time for each I/O, and this will show up in connect time. We call this FICON elongation. When the concurrency becomes severe, these delays can become quite substantial. You will see the typical knee-shaped curve for the connect time as the physical link becomes loaded and contention for the channel or host adapter becomes severe. Open exchanges are the number of active I/Os on a FICON channel. In the early days of FICON, there were some fairly low limitations placed on the number of open exchanges for a channel, and contention might be seen well before that limit was ever reached. For example, on a 4 gigabit FICON channel, you could start seeing quite a bit of FICON elongation at 12 open exchanges, even though the limit is 64 open exchanges. However, with ZHPF, the open exchange limit is well over 600 and is not something to worry about. Pen time is divided into components by RMF. In general, the most useful component of pen time to pay attention to is command response delay, or CMR. CMR tells you how quickly the disk storage system can turn around host commands. When CMR is high, this indicates that something on the front end of the storage is becoming overloaded. So how do you know if CMR is too high? If you look at CMR values from a time period when activity to the storage box is low, this can establish a baseline. Note that distance between the host and storage will add to CMR at the rate of 1 millisecond per 100 kilometers. Generally, CMR values should be fairly stable and not show much variation. Thus, a CMR much higher than the baseline tells you something. Typically, a high value indicates that a front-end resource such as a host adapter or storage processor is overloaded. To confirm this, look for correlations between CMR and DSS throughput measures, especially write throughput. This chart shows baseline CMR for 3 different generations of storage technology. You can see that newer and faster disk storage systems result in lower CMR values. CMR is a good indicator of disk storage system contention across all storage technologies. These two graphs show the correlation between the CMR and the overall DSS throughput for 2 different generations of storage. In both cases, the correlation is very good. Note that the exception is HDS storage, because they put time associated with connect time elongation in the CMR bucket. It is not unusual to see higher CMR on HDS storage. One of the metrics that IntelliMagic has developed is FICON effective data rate. Let me explain how that works. To calculate the FICON effective data rate, we simply accumulate all of the data transferred on the storage system and divide it by the accumulated connect time. Generally, the FICON effective data rate will reflect the level of technology of the storage and channel subsystem. For example, 8 gigabit ZHPF will tend to have substantially higher FICON effective data rate than 4 gigabit FICON. This slide illustrates how the FICON effective data rate varies across 3 different technology levels. You can see how newer technology can improve the efficiency of your storage throughput. Earlier, we had discussed FICON connect time elongation. One way to find times when connect time elongation is happening is to plot the FICON effective data rate together with the connect time. If you see peaks in connect time that correspond to dips in FICON effective data rate, that indicates that the connect time elongation is happening. This chart shows several instances of elongation happening over a few days. This could be an indicator that additional front-end resources are needed. At one time, all of the storage performance reporting in RMF was done by the host. Today, the storage systems also collect performance data themselves and report it to RMF. One example of this is the front-end link statistics. The disk storage system keeps track of link performance data for all FICON, fiber, and replication links. For each link type, it tracks read and write megabytes per second, ops per second, and link response times. The link response times only include the time the link is actively engaged in sending or receiving data or commands. These link statistics are inserted into the RMF Type 74.8 records. All 3 ZOS storage vendors now support collection of link statistics in their latest levels of hardware and microcode. And yes, you can monitor open storage or replication target links from ZOS by just having one volume online to a Z host. Here are some details on how the link statistics are collected and what is included. The read and write megabytes are counted in increments of 128 kilobytes. Each command that goes across the links is counted towards the read and write operations. Thus, it is not uncommon for the link ops per second to be much higher than the I/O request rate, since each I/O request may contain several commands. The service times are accumulated based on how long the link is actively processing each command. This does not include all of the overhead on the host adapter, as there may be some asynchronous processing that goes on. When the link sends data over an extended distance through a FICON director or DWDM, dense wave division multiplexer, the distance latency will be included. If a channel extender is in use, then the link time only reflects the time between the disk system and the channel extender port. The port response time will vary depending on how much data is being transmitted. This chart shows that the port response times are tightly correlated with the size of the data transfers. One way to look for front-end contention is by computing the port intensity. This is simply the product of the port ops per second and port response time. High port intensity likely means that the host adapters are becoming saturated. As a rule of thumb, port intensity greater than 4 could indicate that more host adapter resources are needed. However, for ports that operate at a distance, such as those used for async replication, this metric is not so useful. That is because the distance latency does not reflect time that the host adapter is actually busy. Thus, you could have a false positive if you rely on the port intensity metric in that situation. Similar to the FICON effective data rate, we can also compute effective data rates from the link statistics. This chart shows an example of that. In general, the effective data rate for reads will be higher than for writes. This makes sense because the host adapter sends write data to 2 different memory locations for resiliency. So how else can we tell if a host adapter is overloaded? A host adapter can generally handle only a certain level of throughput, regardless of how many ports are in use. You can aggregate the throughput, ops per second, and response times for all the links to come up with adapter level measures. In general, the adapter response times will correlate well with the adapter throughput. If you see a spike in response time that correlates with a peak in throughput, this is a good sign the adapter is overloaded. This chart shows a plot of host adapter throughput and response time. As you can see, the correlation is quite obvious. Another thing to watch out for is host adapter imbalance. This chart shows an example where there are 16 host adapters on a disk storage system, but only 8 are doing the majority of the work. The active host adapters show elevated response times. Simply balancing the load across all the available host adapters should flatten the response time. The next thing to consider is the middle layer. The middle layer includes things like the internal paths, cache, logical structures, and processors that manage the storage. An understanding of the middle layer can help you answer performance questions associated with these components. One of the common performance metrics provided by RMF is disconnect time. At one time, disconnect only represented the time it took to retrieve data from the disk. Today, any delay time associated with synchronous mirroring also is accumulated in disconnect time. So just looking at the disconnect time may not tell you very much. To help better understand what is going on, IntelliMagic has developed a methodology to dissect disconnect time into components. Using the back-end hard disk drive metrics, the contribution of read-miss staging time can be estimated. Using the replication link statistics, the contribution of synchronous mirroring can be calculated. Any remaining disconnect time may be attributed to queuing and delays. In this chart, you can see that there is a spike with quite a bit of unexplained disconnect time. This is likely because of a peak workload that caused path contention. If you see a constant high level of disconnect queuing and delays, this likely means that some component in the middle layer is overloaded. With DASD fast write, you should almost always see 100% write cache hits. This is because, with few exceptions, data is written directly to cache and destaging happens later asynchronously. However, if the backend drives are temporarily overloaded, the portion of cache allocated for write data may begin to fill up. If the situation persists, host writes will be delayed to allow destaging to free up write cache space. When this happens, the fast write bypass counter is incremented. Actually, the name is a carryover from the past. Since all writes now flow through the cache, a better name might be fast write retry. With today's hardware, this does not happen very often, but it can be common on older hardware or even current hardware with slow or overloaded disks. You also might see elevated DFW bypass when doing a massive point-in-time copy operation, since that could put a heavy demand on the back-end disks. If you frequently see non-zero DFW bypass levels, this is not a suggestion that you need more write cache. It is typically an indicator that you need more or faster disk spindles. Every performance person should know that the best I/O is one you never have to do. A corollary to that is that the next best I/O is a cache hit. The latency associated with a cached hit is an order of magnitude faster than the time it takes to retrieve data from any disk. Even a solid-state drive is slower than cache. Although caches have become much larger over time, you still want to know how much cache is enough. In general, larger storage capacities call for larger caches. For a given workload, a higher cache-to-capacity ratio will produce a higher hit ratio. However, when comparing different workloads, the locality of reference also has some bearing on this. The chart shown here is a comparison of read-hit percentage for two storage systems with different cache-to-capacity ratios. You can see that the higher cache-to-capacity ratio does not always guarantee that you will have the better read hit percentage. Cache residency time is another metric that can help you determine if you have enough cache. The longer that data spends in cache, the more likely it is that the data will be revisited by an application. Using the same example as the previous chart, you can see that the higher cache to capacity ratio tends to have higher cache residency time. In both cases, the residency time is healthy and well over the rule of thumb, which is a few minutes. Parallel access volumes, or PAVs, are a mechanism to avoid IOS queue time. For the most part, PAVs have effectively eliminated IOS queue time at many shops. But how do you know that you have enough PAVs? If you are using hyper PAVs, then the hyper PAV wait rate is a useful metric for verifying that you have enough. In the chart, we see that there are some instances where the hyper PAV wait rate is elevated. If you see significant spikes in hyper PAV wait, as well as some IOS queue time, this could indicate more hyper PAVs are needed. In the chart, we are looking at a particular SSID on a disk storage system. We see that in this case, the hyper PAV wait correlates with the higher IOS queue time. Next, we will discuss the back end of the storage system. The back end includes the drives used to store data, as well as the adapters that move data between the drives and the cache. Since drives are often the largest source of latency for an I/O, it is important that they are not overloaded. First, we will consider what kinds of I/O cause back-end activity and whether that activity is synchronous or asynchronous. Random read hits do not involve the back end at all, as they only touch the cache. Random read misses access the physical drive and are synchronous, so the latency matters. Random writes go straight to cache and are staged asynchronously. Thus they use the drive, but not right away. Sequential reads and writes access the drives, but generally are asynchronous. Pre-staging and destaging are used to avoid the drive latency from adding to the I/O response time. One way to see how efficiently a storage system is behaving is to compare the number of front-end to back-end I/Os. When there are a lot more front-end I/Os than back-end I/Os, this is a healthy situation. This chart shows an example of the healthy situation, as well as an unhealthy situation where the back-end I/Os are sometimes higher than the number of front-end I/Os. Much like the link statistics, disk storage systems also report back-end performance data. Back-end throughput, ops, and service time is reported for RAID arrays, called ranks, and storage pools, which is a collection of ranks. The ranks are reported in RMF type 74.5 records, and the storage pools in 74.8 records. Both IBM and HDS storage provide rank statistics. EMC also provides back-end response, but their design does not fit the rank model used by IBM and HDS. When looking at the back-end data, the two most important things to consider are balance in the use of resources and the average read service time. As a rule of thumb, when the back-end read service time exceeds 25 to 30 milliseconds, the hard disk drives are approaching 100% utilization. When it comes to hard disk drives, the throughput in terms of megabytes per second may not be the best indicator of health. That is because the drives can push much higher throughput for large sequential transfers than for small random ones. You could plot the read and write megabytes per second from the backend statistics as depicted in this chart, but it may not really tell you very much. Alternatively, you can look at the read and write ops per second as shown in this chart. In general, the ops per second per drive is a much better health metric than throughput. Finally, the backend response time statistics, especially the read response times, are the best indicator of how busy the backend drives are. For hard disk drives, When the read response time reaches 4 or 5 times its nominal response time, as seen at low load rates, this indicates the HDDs are close to saturation. The write response time is less critical since most writes are asynchronous. Also, IBM reports the backend write response time on a logical write basis, so it may include the sum of several RAID operations. Thus, write response times may be 3 or 4 times what the read response times are, and this is completely normal. Tiering, both automatic and manual varieties, has resulted in backend storage that may include a mix of hard disk drive capacities and rotational speed, along with some quantity of solid-state devices. If you have such a backend, you may want to see how the different tiers behave in terms of some of the backend metrics. The top chart on this slide has the backend read response time by tier for the hard disk drives as well as the SSDs on the disk storage system. On the bottom slide, it is broken down further by drive capacity. In this case, the 300 gigabyte HDDs and the 400 gigabyte SSDs are in an easy tier pool, while the 900 gigabyte SSDs are in their own pool. This kind of view is valuable when you have backend latency issues, so you can hone in on which drives may be the source of the problem. Remote replication has become commonplace in modern mainframe storage installations. Both synchronous and asynchronous replication have their own set of performance challenges. From sizing bandwidth requirements to monitoring key replication metrics, performance data can be very useful. When a disk storage system does remote replication along with normal I/O processing, this puts additional load on a number of the storage components. For example, the processors and paths inside the storage system will have more overhead to manage replication. Although there is no direct way to monitor this, you can see stress indirectly via the pen CMR and disconnect queuing and delays that I have already covered. Monitoring the peer-to-peer connection data provided in the front-end statistics also provides useful information. Finally, if you have at least one volume on the replication target system online, you will also be able to collect front-end and back-end statistics for the target. This can be very valuable, as sometimes a replication issue can be the result of a bottleneck on the target, such as overloaded disk drives. Earlier, we discussed how disconnect time could be dissected into components. This chart shows the disconnect time breakdown for a disk storage system that is doing synchronous replication. The yellow portion of the graph shows the contribution due to the synchronous mirroring. In this case, we notice some queuing and delays from time to time. These indicate that this storage system may be getting overloaded during these intervals. Since the ZOS host typically is uninvolved in a peer-to-peer replication, you won't get any information on the links from the channel report. Instead, you will get the link statistics from the Type 74.8 records. In addition, you will get a count of peer-to-peer tracks written by volume in the Type 74 subtype 5 records. This chart shows a plot of the replication send response time. We can see several peaks in the response time, which may be caused by large data transfers or delays due to contention on host adapters or the secondary disks. From the front-end link stats, it is fairly simple to compute the average transfer size by dividing the megabytes per second by the ops per second. This chart shows the transfer size and how it varies over time. Having visibility to performance data on the target drives can help you spot issues that may cause pushback to the source volumes. In this example, we see that one RAID array is having high response time. With synchronous replication, this could translate to delays that will elongate response times. IBM Global Mirror is an asynchronous replication method. With Global Mirror, statistics such as the recovery point objective or RPO may need to be watched carefully. Global Mirror data is not reported to SMF natively, but this is possible for those running globally dispersed parallel sysplex or GDPS. GDPS can cut a custom SMF record with default type 105 that includes GM session data, including RPO, as seen in this example. IntelliMagic Vision can digest GDPS records and produce numerous reports. What causes high RPO? If you look at replication send throughput, there will often be a correlation with RPO. This may indicate that provision to intersite bandwidth is not sufficient to keep up with demand. When you see throughput spikes like these, they are sometimes caused by just a few volumes that are running very high loads. Drilling down to a throughput breakdown by volume may help you determine the source of the spike. Disk storage systems are providing a lot of performance metrics via RMF. Although this data is very useful, it can be pretty difficult to wade through. One option is to produce your own code to display the data in a concise and understandable format. Or you can use IntelliMagic Vision, which already does this and more. Besides just presenting the data, Vision provides additional calculated metrics as well as intelligent thresholds for key statistics. If you'd like to find out more about IntelliMagic products, please visit our website. Please contact us and we can arrange a product demo or discuss how to start an engagement. I hope you found this presentation interesting and useful. Despite the popular perception that mainframe storage specialists are dinosaurs, there are a lot of new and innovative things happening on the performance front. Thank you for attending.